In this video, I'm going to show you how to run a MANOVA in R, as well as how to run a few additional assumptions that are necessary in running a MANOVA versus whenever you do an ANOVA. All right, so the first thing that I want to point out, and as you saw on the previous screen, there are a few additional packages that I have found useful in checking these assumptions. So first of all, I always use Rio and Tidyverse for importing data, for handling of data. HE plots, I'm using that in order to get the partial eta squared value, because that is not something that is a default output whenever you run MANOVA using base R. And the car function or package in order to run Levine's test for homogeneity of variances at the univariate level. The myComper package, this is helpful for checking assumptions of normality. The MVN package and the BioTools package, each of those actually are required for the myComper package, but they also each have their own separate functions that are helpful. The rstatics package makes it really easy to run pairwise comparisons as a follow-up. And then the psych package is helpful for getting descriptives using the describe by function to separate the descriptives out by group. So once you import the data, and I'm using a subset of PISA data here, you can see the names of these here. So we're going to be using the PV1 Math, PV1 MACC. This is the algebra subscore, and PV1 MACS, which is the geometry subscore. And then for now, we're going to focus on just having two groups. So we'll use the variable called female, which has ones indicate female, zeros indicate males in this variable. All of these variables are numeric variables, so they've been recoded as ones and zeros, or they are continuous variables. So in most cases, actually, working in R, you don't need to put things as a factor variable in order to get R to recognize it if it is dichotomous. All right, so the first thing that we might want to do is just look at this, and here's the structure here. You can see everything is numeric, all the variables. And you can run some tables or things like that if you want to see what else this looks like. So running these descriptives, which the question here is, do males and females score differently on algebra and geometry subtests or subscores? So we have to run the descriptives separately for each of the two dependent variables, PV1 MACC and PV1 MACS. So for algebra, this first one here, you can see group 0, so this is the males score, so they have a mean score of 492. Skew and kurtosis values look like they are in check, so probably no normality issues at the univariate level for that group. And then group 1, these are the females, and they scored slightly lower, 484 mean score. Skew and kurtosis values also look reasonable, very close to 0. Actually, they're a little bit more normal than the males. If we look at the geometry scores, we see that the males had an average score of 470. Skew and kurtosis values also look reasonable here. And for the females, they also scored lower, 459. And skew and kurtosis values look okay here as well. But then we could also look at histograms for visual inspection. And so by adding this component to the geom histogram line, as well as this stat function um, component here, which we're going to get a normal distribution. So that's what this d norm means, with the mean being the mean of this variable and the standard deviation being the standard deviation of that variable. So if something had the same mean as standard deviation, what would the distribution look like? And it draws the distribution on it. And then this facet grid breaks up the plots based on the groups, males and females. So if you look at the plot down here in the lower right corner, you see for males, it looks pretty good actually. Maybe slightly skewed to the right, but it's extremely slight. Same thing with females. Looks like kurtosis value may be a little bit off. Kurtosis is like the peakedness of the distribution. But otherwise, it looks pretty good. It's kind of giving us the same information the skew and kurtosis values give us. And if we do the same thing for the geometry subtests, we get a similar picture. So actually the males distribution looks even tighter, closer to that normal distribution. And the females maybe look slightly skewed to the right. Things are a little bit off on the left side here. But otherwise, it looks pretty good, actually. It looks like we shouldn't be concerned about normality. And of course, remember, we have thousands of people in this data. So the next thing we want to check for is multivariate normality. So the first thing we can use is this MVN function, and it stands for multivariate normality. So we can't use the dollar symbol with this function for some reason. It does not allow that. So you need to call the column numbers that are associated with the algebra and geometry subscores. So in this case, those are columns 2 and 3. The second thing in the function is to call to have the QQ plot printed at the multivariate level, and this is interpreted at the same way as a univariate QQ plot. And then this multivariate outlier method, QUAN, is using Mahalanobis distances, which you can interpret this similarly to a z-score. So if values are very large, it indicates that they're far away from the mean and are considered outliers. And this is doing this at the multivariate level. So it's looking across both of these dependent variables. And if we do that, one of the things that gets output here is first, it by default will choose this statistic called Mardia skewness and Mardia kurtosis. It's looking at both of them and providing us with a statistic and a p-value associated with each of those here in order to tell us if things are normal or not. And the same thing applies as with other normality tests. So the null hypothesis here is that that things are normally distributed. So here we see a very small p-value for skewness, indicating that probably it is the skewness fails, basically. It fails the test. Skewness is too much deviating from normality, and kurtosis is not. So this is what this is telling us. No, there is not normality. Yes, there is normality. That's what that's trying to help indicate. However, if we look back at we think back to our plots, it didn't look like it was. And remember, we have very large sample sizes, so this could be an issue, and we have another thing we can look at here in a moment. But it also spits out two other plots for us to look at. So here's the QQ plot. Notice things look pretty good. There's definitely fewer points out here, and those could be outliers. And if we go to the next plot, which shows us where the cutoff is for the outliers, so it's using this cut point of 7.378 for the Mahalanobis distance values. So in red, it's put these outliers out here, and it's saying that there's 131 outliers out of 4,900-ish observations. So There could be some issues with outliers, and maybe that's part of why we're also getting that there's this skewness value that's being that's being thrown off. So the next thing that we could do is look at the other tests that are involved. So there's actually 4 different multivariate normality tests that you can run. So H, Z, D, H, and I haven't been able to get energy to work again. For some reason, it's getting hung up. So, but it worked for me earlier today. But if we run these, we get another set of, and these are spit out as well, but it's using Shapiro-Wilk, which is not really helpful for having such a large sample size, even though it's giving us telling us that there's no issues at the univariate level, and some descriptive information. Okay, so HZ is Henze-Zerkler test. It is also telling us that we appear to have abnormality. That statistic is less than 0.05. P-value attached to it. And if we go down to the DH, Dornick-Hansen, we see a p-value not greater than 0.05. So it seems to be that there is some consistency in this being abnormal. However, if we look at this, the QQ plot, it seems to be that maybe the issue is with a few of these outliers that are causing some problems with skewness. And yet 2 of the tests are telling us, or 1 of the tests is telling us there's no issues, but the others are telling us that there are. All right, so then we can go on to looking at some other things. So first of all, we need to examine homogeneity of covariances. So to do that, to use that, we have to first make the female variable a factor variable. Right now it's numeric. So change that to a factor. And then we have to remove NAs in order for the function to work. So I just stored it into a new variable I called PISA 2 because I'm only going to use that just for this particular test. And this one is a good one to be able to run, but you need a sample size of less than 2,000. So because we have more than 2,000, it's not going to work. And it will spit out some information that we've already seen from the MVN. So the other piece of information that we really need is just boxes M, which is a measure of homogeneity of covariances. Are the covariances the same? So with an ANOVA, we run Levine's test a lot for homogeneity of variances. So since there's multiple variables now, we need to look at homogeneity of covariances also. So that's what you can see here, the output from that. So the p-value is 0.02, which is telling us that there's potentially a problem here with homogeneity of covariances. If we look at the Levine's test output, which this is using the CAR package, Levine test, and you just put the 2 different variables in here. So the first one, which is for the algebra scores, is telling us that the variances appear to be not equal for group 1. And then it's telling us here that that we don't have equal variances for the sorry, I didn't mean to say group 1 for algebra. And then this one's for geometry, that there also appears to be some issues with homogeneity of variances at the within geometry. We also need to check linearity of the dependent variables. So one thing we can do is just look at this plot here. This is just a scatter plot with algebra scores on the x-axis and geometry scores on the y-axis. This is telling it that you should be using points and to separate the plots by male and female. So if we look at this plot, it looks really good. Looks pretty linear. Doesn't look like there's a curved relationship of any kind, like a quadratic or a exponential function. It seems like a straight line would work well. And then we can look at the correlation of the two variables together, which appears to be quite high, a correlation of 0.885. And depending on what you read, some places will say that you need a cutoff of 0.9. Some will say a cutoff of 0.8 means that there's too much correlation between them. So that could be problematic as well. And after that, then we're ready to run the actual MANOVA. So all of that was just additional assumptions beyond what we would normally do. I've included a few of them, ones you would do for an ANOVA in there as well, though. First, you just use the function MANOVA, and you have to combine the two dependent variables together using what's the function cbind. This basically creates these two into a matrix. So it's looking at two columns at once as the outcome measure, if you will. And then just like you would with a linear model, you use the little tilde symbol and then put the grouping variable, in this case, female. And we're going to store that into M1 and then get a summary of it. So just summary of M1, and we can tell it which test to use. If you don't specify a test by default, it will use PISA trace. And that one is useful sometimes. For what I'm doing right now, I'm just going to go with Wilks because it's more widely known and used. And if you look at that output, it will give you the statistic for Wilks lambda. And it will give you the p-value here, which is quite small. And so this is indicating to us that there is a difference somewhere. So at the multivariate level, looking at everything from a global view, there is statistically significant differences. And then we want to know, well, how well does this multivariate model actually explain those differences? That's what the eta squared is for from the HEplots package. So that is telling us this value here, which this is interpreted like multiple r squared. So this is telling us that 0.3% of the variance in the outcome measures is being explained by group membership. In other words, whether someone is male or female explains about 0.3% of the differences we see in algebra and geometry subscores. Not very much. And then we can run follow-up ANOVAs to see where that actually those differences exist. And so luckily this is really simple to do. Summary.aov will pull out the ANOVAs from the MANOVA. And you can see response 1. So we have PISA female and probability, the p-value is 0.003. So statistically significant there. And if we scroll down, response 2. So if you remember, response 1 is not whether it's male or female. Response 1 is the first outcome measure, and that was algebra. So response 1 is talking about PV1 MACS, the algebra scores, males and females, according to an ANOVA, that's a follow-up test. Males and females scored statistically significantly different. And then we can see response 2 for geometry. They also scored statistically significantly different from one another. And we could look at the differences in the means of these two in order to make more sense of that. And that is it for 2 groups. So let me know how this goes and feel free to reach out.